Okay, so let's continue on to cache coherency. So for Wittigon, it's okay to just check the recording, I think. And if you have any follow-up questions about the things we talked earlier in the last 30 minutes, let me know. All right, but for now, we'll move on to coherency issues, which kind of involve, well, actually, let me motivate what is this first, right? So let's say you have a multi-processing system, right? You have a shared cache. This shared cache can be distributed across multiple cores and can be modified by also many applications. What do I mean by that? Okay, let's say if I have the processor P1 and processor P2, right? And I have each of these processor has its own private L1 cache, and you have to share L2 cache. Okay. And let's say both of these want to access address X, right? And the sequence is this: processor 1 read address X, processor 2 write address X, processor 1 want to read address X. All right. So basically, I have read from processor 1, then write from processor 2, then read again from processor 1. This is the sequence in time, right? So this is the sequence in time. What is going to happen? So when processor 1 say, I want to read X, what's going to happen is L1 will have the data X, right? Let's say this is address X. And let's just assume that currently X, the value is 5, and I want to write 10 to that, right? So processor 1 will have the value 5 here. L2 cache is going to have value 5 here, all right? Then for processor 2, I said, I come in and say, I want to write to X, right? So I would first bring X into the L1, same address X in the L1 of the processor 2. I write to it, so the value is 10. Now, processor 1 comes back and say, I want to read X. Is that a hit in the L1 cache? คำถามนะครับถ้าเป็น situation เนี้ยตอนอันที่ 3 ที่บอกว่า processor 1 จะต้องการอ่านค่า X อ่ะมันจะเป็น cache hit ใน L1 หรือเปล่า That's going to be a cache hit, right, in the L1 cache. Processor 1 haven't even modified X, so that's not dirty, right? And it's going to be a valid cache hit request. It will read the L1. And what's the value it's going to read right now? If you are processor 1 and look at the L1 of your own and say, hey, it's a cache hit. What is the value you're going to read? Is that 5 or 10? ถามอีกรอบ processor 2 บอกมาแอบแก้ค่าจาก5 เป็น 10 แล้ว processor 1 ก็ไม่รู้ เพราะว่า processor 1 ก็มีค่า 5 อยู่ใน L1 cache ก็ hit แล้วก็บอกว่าเจอค่า 5 เอาค่า 5 ไปใช้เลย So this is the problem with coherency, because in this case, the L1 cache, from processor 1 point of view, even though it's a totally legit cache hit, the data is not updated, right? Because ideally, at some point, if processor 1 wants to use the L1 cache data, it needs to be informed that, hey, processor 2 actually modified this, so it actually write 10 to processor 1's L1 cache, right? Now, any questions so far? มีคำถามไหมครับสำหรับปัญหานี้เอาแค่ปัญหานี้ก่อนเดี๋ยวเราจะไปดูว่าแก้ยังไงมีคำถามไหมครับหรือเคลียร์ให้โอกาสนั่งงง1 2 3 4 5เคลียร์นะ Okay. So let's assume we are all clear on this. If you're not, let me know as soon as possible. Okay. So the question is, how do we maintain coherency of the state of my cache for all the different caches, right? So the high level idea is this, right? The problem we solved earlier was that the cache line are not aware that it's being modified by someone else. Basically, another processor modified the cache. And processor one, I was like, I'm not aware, so I will use the old data, which is wrong, right? So the high-level idea to impose coherency is I will add a status to each cache line. Now, each cache line will have the spatial coherent status. If the block is read-only, it basically means that no one write to it. I can access the data as I want, right? Then, if there are write to the cache, that will modify the status depending on what's actually happened, okay? Depending on what actually happened. This is going to be called the cache coherent protocol, okay? It's going to be called the cache coherent protocol ก็คือไอเดียก็คือว่าแต่ละ cache line เนี่ยเราจะมี status tag เข้าไปเลยปึ๊กแล้วบอกว่าถ้าบล็อกเนี้ยมันเป็น read only คือไม่มีใครเขียนค่าทับทุกคนใช้ได้แต่ถ้ามีใครสักคนเขียนค่าทับเราจะต้องเปลี่ยน status เราบอกว่าเฮ้ยเราต้องเอาอัปเดต data สักจุดหนึ่งเราต้องอัปเดต data ตรงนี้ถ้าเราจะใช้มันเพราะว่า data เป็น data เก่านะครับ so that's called the cache coherent protocol And the goal in terms of design, we basically need to design a protocol that works, right? So it's actually not hard to make a protocol that works. Every time I write, I update everyone's cache, right? But that's bad because that means that I'm going to send a lot of updates to all the cache. So there'll be a lot of communication. There'll be a lot of data transfer. The goal is how do we minimize this? How do we increase the latency? Oh, actually, decrease the latency of a read and consume less power per request, right? I want to minimize communication data transfer. So a quick idea again, and I really want you to get this part is, if someone modify the data that I have in the cache, I need to be aware that eventually I have to update the data, okay? So one thing I can do is I can invalidate the processor cache data if they are write to the block on the processor. So the way to implement this is I need the ability from my processor, basically where I am, to be able to see someone else's action. We call this, we can use a bus for this. Basically, a bus connects all the processor and say, if someone write to it, I need to be aware. So if someone write to it, I would signal that through a bus. We call this the Snoopy bus, because literally what we're doing is we snoop around and see, are there anyone that write to the cache, right? Then here's basically the earlier example, the same thing, right? I want to visualize this. I have read from processor one, read to X. Then I have write to address X, and then processor one again want to read X, right? And here's the sequence of time, right? So the first read X is going to be in here. The data is 5, right? From the earlier example, the data is 5. Put in the L1 and L2 cache. I write 10 to this. When I write 10, the Snoopy bus, right, will need to basically get triggered, and processor one will say, oh, wait, someone is modifying X. So this will be tagged with stale. Basically, it's like old data I need to update. Eventually, I need to update myself so that if I need to read X again, the data update will happen. Number 10 will get overwritten here. This becomes 10, and then you can read X correctly. These allow you basically read the correct data, right? So the protocol that I will cover next is called, this is the basic, right? We will improve on this, to be honest, in a bit. But the first protocol I need to talk to you is called the MSI coherent protocol. Basically, each block has 3 states. It can be modified, it can be shared, it can be invalid. So my block that address X, right, that has 5 or 10, it can be in one of the 3 states, modified, share, or invalid. What it means is if I'm in a share state, is one of the several copies, and I can use it. If I'm in an invalid state, the line is not there. I don't have the data. If it's in a modified state, I am the only copy, and the block is dirty. I modify this. So actually, I'll use the other example. That's simpler, right? I have processor 1, L1 here, processor 2, L1 here, and then I have the L2 cache, right? And here's a Snoopy bus, right? Originally, I put 5 in address X here. It's going to be in the share state. It's one of the copy. There can be multiple copies. There can be one copy. It's OK. I can use that data. Then processor 2 comes in, say, I want to write to X from 5 to 10. Address X is the same. This becomes modified. I snoop around. Processor 1 snoop around, say, hey, processor 2 modify my data. So I'll change from share to invalid. That's the invalid copy. So P2 modify the value, send the trigger the signal in the Snoopy bus saying, whoever has this block, which is processor 1, change your status from wherever you're in into invalid. Now, processor 1 is in the invalid state. I want to read X. I now know that whoever has the modified state has to forward the data to me from 5. Now I forward the data to 10. I can then transition from invalid again to share because I have the data. Processor 2, that's in the modified, right? I just give the data to processor 1, so it's in a share state. It's in the share state. Basically, there are now 2 copies of X. Processor 1 has it, processor 2 has it. Both of them has the correct value. Both of them are in the share state. All right. So that's the MSI protocol. When I have the read miss, I send the request and I transition to share because I just read the data. I now know that I'll be in the share state. If I have a write miss, I will write the data because I only have I'm the only one with a copy. I transition to M. If you see read exclusive, basically means someone write to the same block. I transition to invalid. And the transition from share to modify, from share to modify, right, can be done without reading the data from memory. I don't need to actually go to the memory to actually check, right? Are you all with me so far? ก็คืออันนี้นะครับสมมุติเรามี processor 2 ตัว P1 กับ P2 นะฮะแล้วเราต้องการ modify address X ตอนที่เรามี copy แล้วเราใช้ได้เราจะ copy ที่ใช้ได้มี2 state เป็น share ก็ได้หรือเป็น modify ก็ได้ถ้ามันเป็น share แปลว่าไอ้ copy เนี้ยคนอื่นอาจจะมีก็ได้แต่ว่ายังไม่มีใครเขียนค่าทับถ้ามีใครเขียนค่านี้ทับปุ๊บเข้าไปเนี่ยไอ้คนเขียนทับจะกลายเป็น modify ส่วนคนที่เหลือจะเป็น invalid เพราะว่าบล็อกเก่าที่มีอยู่มันเป็นค่าเก่าแล้วมันใช้ไม่ได้มันจะกลายเป็น invalid เสร็จแล้วถ้าเราจะต้องการอ่านค่านี้เดิมแล้วมันเป็น invalid มันก็จะไปบอกใครมี modify เอาค่ามาให้ใส่ดีๆแล้ว invalid มันจะกลายเป็น share เพราะว่าเราได้ค่าใหม่แล้วส่วน modify ด้วยความที่มันเพิ่งให้ค่านั้นไปกับเพื่อนมันก็จะกลายเป็น share นะครับมีคำถามไหมมีใครงงไหมดีกว่าเรามาลอง state transition กันดีกว่า let's actually try the state transition diagram right I have the possibility of I'm in a share state modified state or invalid state for the block right if I am in a share state and someone else read so if you probe read you're in the share state because someone else just need the data no one modify the data if I'm in a share state you go to invalid it's not valid anymore someone just modified the data right if you're in a modified state you see someone else write to the data you go to invalid because your data is not valid anymore If you are in the modified state, someone else read the data, you transition to share because now you are sending data over. So if you probe read, then you actually forward the data. Right? You forward the data to the other processor because, hey, you need the data. Here's the data. If you're in the invalid state and someone read or someone write to the block, you stay there because it doesn't matter. You're not doing anything, right? You probe, read, or write. If you're in the invalid state and you are on your own, you read the block, you are going to transition to share. If you're in the invalid state, you write to the block, you go to modify. You write to the block, you go to modify. Then you signal everyone, I'm writing. If you are in a share state and you're reading, you stay there because you're not modifying the data. If you're in a share state, you write to the block, you go to the modified. If you are in the modified state, you read or write, you are in a modified state. All right. That's when things get complicated because if you look at the state transition diagram, there are so many arrows. The key idea is you can have, you are moving because of two actions, two possible actions. You're probing something happen, or you on your own are doing something. And that something can be a read or a write. alright ก็คือคอนเซปต์ก็คือว่ามันจะเกิดขึ้นได้2แบบเราคนอื่นทำอะไรสักอย่างกับตัวเราเองทำอะไรสักอย่างไอ้ทำอะไรเนี่ยมันเป็นได้2กรณีแตกย่อยขึ้นมาก็คือการอ่านกับการเขียนถ้าเราเห็นคนอื่นเขียนเรากลายเป็น invalid เพราะเราจะไม่มี copy อันใหม่ถ้าเราเห็นคนอื่นอ่านมันขึ้นอยู่กับว่าเราอยู่ใน transition แบบไหนถ้าเราอยู่ที่ modify คนอื่นอ่านเราเอาค่าใหม่ไปให้เขาแล้วเรากลายเป็นแชร์ถ้าเราอยู่ในแชร์คนอื่นอ่านเราอยู่ที่เดิมก็คือแชร์เพราะว่าก็มีอีกคนต้องการอ่านค่านี้เราก็จะมี copy เนี้ยก็จะเป็น copy ที่ valid อยู่นะครับถ้าเราอยู่ invalid คนอื่นอ่านคนอื่นเขียนอย่าไปยุ่งกับมันเราไม่ได้ใช้อะไรนะครับถ้าเราเขียนเองแล้วเราอยู่ในแชร์เรากลายเป็น modify เพราะเราจะมี update copy คนอื่นจะกลายเป็น invalid นะครับถ้าเราอยู่ในแชร์แล้วเราอ่านไม่เกิดอะไรขึ้นเราอยู่ที่เดิมถ้าอยู่ invalid เราต้องการอ่านเราจะกลายเป็นแชร์เพราะเราจะไปดึง copy อันใหม่มาเราก็บอกว่าเอ้ยแชร์กันส่วนคนที่ forward copy มาให้จะเปลี่ยนจาก modify เป็นแชร์ถ้าเราอยู่ invalid แล้วเราเขียนเราจะไปที่ modify แล้วเราไป invalidate คนอื่นก็คือเราไปที่ modify แล้วคนอื่นจะกลายเป็น invalid เพราะเราจะเป็น copy เดียวที่มีอันใหม่นะครับคำถามให้วิธีทำข้อพวกนี้หรือวิธีการ follow logic พวกนี้เอาง่ายที่สุดก็คือว่าเราแค่ต้องดูว่าไอ้ copy ที่ valid อยู่กับใครถ้า action นี้เกิดขึ้น copy ที่ valid อยู่กับใครถ้า action นี้เกิดขึ้นนะครับ so basically we just need to care who has the valid copy if certain action happens are there going to be more than one copies if there are more than one copies they're going to be in a shared state if there are only one copy in this case it's the shared state so now here's the downside of the MFI protocol when I read I go to share even though it might be the only copy in the system I might be the only guy with the copy right so what if I just don't want to notify others right so the key idea here is well I can optimize this because I don't have to tell everyone else that I have the copy if I am the only owner of that copy right so the next optimization is the modification to the MSI protocol into the messy coherent protocol, which is basically one of the textbook coherent protocol, if you will, right? This consists of 4 states: modified, exclusive, share, and invalid, right? The addition here is modify used to be I have the only copy and it's dirty. The exclusive is the addition that I have the only copy and I'm reading I haven't modified the data. All right. You see how that would change diagram. Okay. The key idea is I can transition from exclusive to modify without telling anyone because no one else has a copy. I don't care. No one else has that block. I just transition to E to M silently. So when I have read and write, like write is going to modify the data. So read needs to get the most updated copy. You always think about this. If someone write who will have the valid copy, who need to be invalidated. That's it. Okay. Then the key issue is I need to propagate the update data to all the reader, right? This can be flush. This basically is to slow things down, right? So the MESI protocol allow the processor to maintain the state and in some cases silently transition the state from E to M without telling everyone else. So here is the protocol. Again, there are 4 actions, right? I can probe, read, I can probe, write, I can actually do the read, I can do the write. And this is basically used in Intel Pentium Pro, okay? The optimization on this design for modern CPU. We'll go through that in a bit, all right? But let's do messy protocol first. We'll go one by one, okay? Now, if I am in the modified state, let's say I'm in a modified state. Modify means I have the only copy and it's the dirty copy. I modify the data, so no one else has a valid copy. If I see someone else reading, I am going to transition to share. So this is when you probe, read, and then you also forward the data over. Right, because you have the valid copy, you forward the data to the other copy because here's the data that I write to it. Okay, if someone is reading and in the I am in the modified state. If someone else is writing, I go directly to invalid because whatever copy I have in my cache, right, is not valid anymore. So if you probe, right, do we have to forward the data over? No, because that guy just updated the data. It's not valid anymore. Okay, so we're in the modified state. All right. If we are writing, and we are in the modified state, we stay there because it's being modified. I modify it again. It's going to be modified. If I'm in a modified state and I am reading, I stay there as well. I'm in a modified state. I have the only copy of the data. And I read from it, who cares? No one has the valid copy, so I stay there. Okay? We are done with the modify on all the 4 actions. All right. If you are in the exclusive state, and you probe someone else is reading, it means that you originally have the only copy of the data and someone else is reading. I'll go to exclusive to share. So if you probe read, and the L2 have the updated data already, so you do not have to forward there. It's going to be hidden in the L2 cache. If you probe someone else is writing, originally you have the only copy of the data, but someone else say, I want to write to that address, your data becomes invalid. So if you probe, right, it becomes invalid. Okay. If you are in the exclusive state and you read, you stay there. If you're in the exclusive state, you write to it, you silently transition, no communication needed. Right, so this is done internally. You don't have to inform anyone else because you guarantee that that's the only copy. Okay. We are done with exclusive state. If you are in the share state, someone else is reading. You have one other copy, you read it. That's okay, you stay there. So you read, you probe read, someone is reading, right? So you stay there. If you are in the share state, someone else is writing, you don't have the valid copy anymore. You're going to transition to invalid, right? If you are in the share state and you are reading, you stay there. If you're in a share state, you write to it, you are going to go to modify. And again, when you read or write, you send read or write signal to Snoopy bus so that everyone else can then update the state. Okay. The last thing we have to cover is when you're in the invalid state. If you're invalid state, someone else is reading or writing, doesn't matter. You don't have the data. So if you probe, read, or probe, write, you stay there. I mean, it doesn't matter. You don't have the valid copy of the data anyway. If you are in the invalid state and you are reading the data, you go back to share. If you're in the invalid state and you are writing, you go to modify. All right. Any questions so far? Again, we just need to consider all the possible options. And then for all this option, if you are the one taking the action, read or write, to consider for the other block, what do I have to do? Do I have to update the copy or do I have to stale copy the old copy? Then you transition to the correct state. ก็คือภาษาไทยนะครับ ก็คือว่าเราจะมีแอคชั่นได้4อย่างเราเห็นว่าคนอื่นอ่าน เราเห็นว่าคนอื่นเขียน กับตัวเราเองอ่านหรือเขียน ในแต่ละสเตจมันก็จะ transition ตามที่สเตตัสว่าไอ้บล็อกเนี้ยบล็อกใหม่สุดจะมีใครเป็นเจ้าของบ้างถ้าบล็อกนี้มีคนมากกว่า1คนเป็นเจ้าของได้เราจะอยู่ในแชร์ถ้าเราเป็นคนเดียวที่เป็นเจ้าของเราจะอยู่ใน exclusive ถ้าเราเขียนเราอยู่ใน modify ถ้าคนอื่นเขียนเราจะกลายเป็น invalid ถ้าคนอื่นอ่านอันนี้ขึ้นอยู่กับว่าเราไปอยู่ในสเตตัสไหนคือถ้าเราอยู่ในแชร์คนอื่นอ่านเราก็อยู่ในแชร์ถ้าเราอยู่ใน modify คนอื่นอ่านเราจะกลายเป็นแชร์เราต้อง forward data อันใหม่ที่เรามีไปให้เพื่อนนะครับแค่นั้นเลยคำถามครับใครงงแล้วยกมือหน่อยเดี๋ยวเราต่อไปที่อันต่อไปเนาะแล้วเดี๋ยวเรา take long break กันดีกว่า long break เพื่อให้กำลังแบบทำอันนี้เดี๋ยว long break เนี่ยจะมีตัวอย่างจากข้อสอบเก่าเดี๋ยวเอาไปให้ลองทำนะครับเดี๋ยวจะเอามาให้ลองทำแล้วเดี๋ยวหลัง break เสร็จเราจะมาเฉลยกันเนาะ So let's move on. We'll have a sample from the previous year's exam questions. So here's the problem with the messy protocol, right? Well, it's good. Obviously, it's good, better than MSI protocol. But when you need to write the modified data back to the main memory before you share, right? The problem, the reason why this is happening is because when you're in the modified state, right? When you're in the modified state, you have kind of not a lot of guarantee on the ownership. So one thing we can do is we can add the fifth state, the ownership state. The ownership state means that this is the valid copy that I have the exclusive right into. Essentially, this is designated owner. When you are in the modified state, you don't have to do write back yet. The owner, whoever is in the ownership state, if the cache block get evicted, the owner will do the write back for you. Okay. Then this kind of modify the share state a little bit by saying, hey, the share state is share, and the block can potentially be dirty. It can potentially be dirty, but I will avoid the write back to the upper level cache. Because I would let the owner perform the write back only when needed. Okay. อันเนี้ยมันเป็น optimization ภาษาไทยนิดนึงมันเป็น optimization ที่บอกว่าถ้าเรามีแค่ MESI ตอนเราเป็น modify ใช่ไหมครับแล้วถ้าเรา transition เราจะ write back ตลอดเวลาแต่ด้วยความที่เราไม่อยากจะ write back ไปที่ DRAM บ่อยๆมันเปลือง bandwidth เนาะเราจะใส่ ownership state เข้าไปแล้วบอกว่าเวลาเรา transition จาก modify กลายเป็น share มันจะมีตัวหนึ่งจะเป็น designated คนจะเป็นไอตัวนี้จะเป็นคนที่ write back ให้เราคนนี้จะ transition ไปที่ owner ส่วนคนที่มี share state อ่ะคนที่มี share state อ่ะไอ้บล็อกเนี้ยมันอาจจะ dirty ก็ได้ แต่ว่าถ้าบล็อกมันถูกเตะออกคนที่ต้องเขียน write back คือ owner นะครับ so here is the protocol actually let me do some quick thing right let's I think it's blue ink already again the action are probe read you probe right you can actually reading right and you are writing okay let's go one by one all right if you are in let's go start with the share state because share state is I think in my opinion is kind of the simpler one right if you are reading or if you see someone is reading and you are in the share state you stay here you're in the share state no one modified the data you stay at the same place if you are in a share state and you see someone writing if you're in a share state you see someone writing you transition saying I will be invalidated because I don't have the copy of the data if you're in a share state and you write to the block you go to modify right you go to modify now that's it for the share state if you are in the modified state if you're in the modified state and you read or write to the block it doesn't matter you are the only one with a valid copy so you stay here right if you see someone else writing you go to here you go to invalidated right so here you go back to invalidated if you are in a modified state someone is reading originally without the ownership state you transition to share without the ownership state you transition to share and then you do the write back so that it's a clean copy it's not dirty in this case you have the ownership state you're in the modify you transition to owner then you supply the data to the other block right then if you are in the ownership state which means that you have the dirty block everyone else can also have the block if you see someone else reading you stay there if you are reading you also stay there because it's now clean the block is dirty but everyone has the updated copy if you're in the ownership state and you modify it again you are going to transition to modify because now you have a dirty block and you are the only one with the data no one else has it if you are in the ownership state someone else is hitting in the cache and you see that they are writing you supply the data right you supply the data over if you're in the exclusive state basically exclusive mean that's the only valid copy and it's not dirty so if someone is reading or you are reading you stay there if someone is reading you move to share if you're in the exclusive someone is writing if someone is writing you move to invalid because they have the updated data I don't have it if you're in exclusive and you on your own write you go to modify if you are in the invalid state and you write and miss the cache you go to modify you have the updated data and then someone perform the write back right if you are in the invalid state and it's a read I transition to a share if I'm in the invalid state and you are the only copy no one else has the share state you go to exclusive because you are the only one with the valid copy right so that's a special case with the I transition from I to E if you have the only copy you go to exclusive if someone else has a copy you go to share right so that's a Morse protocol right oh I already have this right so let's now talk in Thai again just to recap this ก็คือไอเดียคร่าวๆนะครับเราจะอยู่ในสเตจเนี้ยแต่ละอันอ่ะไอ ownership state จะเป็นบอกว่า เราเรามี copy คนอื่นมี copy เหมือนกัน แต่ว่าเรามีหน้าที่ในการทำ write back ไปบอกแฮชอันบนบอกว่าเฮ้ยพี่ผมมี copy อันใหม่ด้วยนะ ถ้ามันเกิดอะไรขึ้นผมจะเป็นคน write back ให้นี่คือ addition ที่เพิ่มเข้ามาที่เหลือจะคล้ายๆเดิมนะครับที่เหลือจะคล้ายๆเดิมแต่ว่าเวลา transition จาก model ส่วนที่ต่างคือเวลาเราอยู่ใน modify state ถ้าคนอื่นอ่านเราจะไปที่ ownership คนอื่นที่อ่านจะกลายเป็นแชร์คือแปลว่า copy เนี้ยมีอยู่ในหลายๆ cache แต่เราจะเป็นคน write back ให้อันนี้ก็คือจุดต่างนะครับที่เหลือจะเหมือนกันอันนี้ใช้กับ modern CPU basically this policy is used in modern CPU nowadays all right and you would need to assume that this is the case the reason why MOSI works so well is for most of your data in the program you don't share you don't share so in many cases a lot of the data will be in the exclusive and modified and occasionally if it's read only then we go to the ownership and share which allow you to run the computer quite well. It's going to be a lot faster than the MESI and the MSI protocol because you reduce communication. Okay. So before we go to the break, right? Before we go to the break, I'll put the file on class website from the previous year exam. I'll tell you the question that you have to check out and we'll do a quick break. I'll leave the screen up for the MOSI protocol and then you can check the exam out and see if you can go through the questions. All right. And once you're back from the break, I'll do a mini break. Basically, I'll do a quick 10 minutes break. I'll come back, explain the question on the exam. Then you all have the practice time to work on the exam. So there'll be a longer practice time. We will not do the video recording of that because you're basically doing the practice. Then we'll come back. I'll go over the question. Again, we are not going to record that, but we'll go over the questions. Then we'll move on to memory consistency. All right. So let's first do a 10 minutes break. In the meantime, I'll post a question on the on Canvas. All right. So let me stop the video. In the next set of video, we will transition to memory consistency. Okay.